Alrighty. This part of it's kind of review of series. It's kind of not. Some of it will be because we're going to be dealing with properties of sigma, but it's it's only a little bit of limit type stuff, so it's only minimally calculus stuff that you would have seen last year. Let's go ahead and start off with a couple of one theorem and then a test. Now, the theorem, and this is Theorem 6 and 11.2 in your book, it says if the series n is equal to 1 to infinity of a sub n is convergent, then the limit as n approaches infinity of a sub n is equal to 0. And that should make sense to us, right? It can't be convergent if each successive term is not getting smaller. Each successive term has to be getting smaller in order for it to converge. Now notice what this does not say. This does not say if the limit as n approaches infinity of a sub n is equal to 0, then a sub n converges. Okay, that is not what it says, because that is not necessarily true. Okay, so it converges. If it converges, you know that each successive term is getting smaller than the one before it, and those successive terms that you're adding are going to 0. But just because they're getting smaller, doesn't mean the sum converges. They have to be getting small enough, fast enough, okay? And let me give you an example of one that actually does not converge. That does not converge. That is 1 plus 1/2 plus 1/3 plus 1/4 plus da 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 da. Okay, well that should make sense to us if we remember our improper integrals, because that didn't converge either. Okay, so if that didn't converge, then why would that? Okay, this series right here goes by a very specific name, and it pops up every once in a while, and therefore you need to know that it is divergent. This is one where each successive term does get smaller. If I were to actually take the limit as n goes to infinity of 1 over n, that is 0. But just because that is true does not necessarily mean it converges. It means that it might converge, okay? This is what's called the harmonic series. The harmonic series does not converge. It diverges, okay? So this only says that if the series converges, then each successive term is getting smaller towards 0. Now, if you actually flip it around, it actually does become a little bit more conclusive. And this is a test for divergence. It's on 709 in your book in 11.2. And it actually says that if the limit as n goes to infinity of a sub n either does not exist or does not equal 0, and by d and e I think they mean goes off to infinity or negative infinity, or actually doesn't approach. I think that includes infinity or negative infinity. Or it doesn't equal 0. Basically, if basically you know that each successive term is not progressively getting smaller, then sigma n is equal to 1 to infinity of a to n is divergent. So the flip side actually is a little bit more powerful, okay? So I know that if each successive term is getting larger, it's going to be divergent, okay? Or, or if it's just not getting any smaller. If it's going towards some sort of finite number that is not 0, it's not going to converge. Because even if it's a very, very small number, like like 1/10, if you add up an infinite number of 1/10s, it's not a finite number, okay? So let me go ahead and do an example. This is actually a really good one in your book. And the reason I'm showing this one to you is the fact that it actually, once you get into more robust tests, you're going to feel inclined to use the more robust tests, and you're actually going to forget this very simple test for divergence. Because, what we've done so far, you're like, oh, okay, well, I don't know. Let's see if we can change the form. How about natural log of n squared plus 1 minus natural log of 2n squared plus 1? Oh, I wonder whether it's telescoping. Okay, well, let's see. We'll go ahead and plug in 1, and we're going to get natural log of 2 minus the natural log of 3. Okay, well, let's see what happens in the next iteration. Let's go ahead and that's natural log of 5 minus, and we plug in 2 here. We're going to get natural log of 9. No, it's not looking like it's going to be telescoping. Go, okay, well, the natural log of plug in 3 right here, we're going to get 10. Plug in 3 right here, and we're going to get 19, natural log of 19. Okay, that's not telescoping. That's not going to collapse, right? Because none of the terms are actually canceling each other out. Well, I tell you what, why don't I try another tack? Why don't I just take the limit as n approaches infinity of the natural log of n squared plus 1 2n squared plus 1. And basically I know that that's going to wind up being the natural log of 1/2. Well, whatever the natural log of 1/2 is, it ain't 0. And so if each successive term is getting closer and closer to natural log 1/2, then each successive term is simply, once you get on to really, really large numbers, you're functionally adding natural log of 1/2 in each successive term. Well, you can add up an infinite number of natural log 1/2s, and it's just going to be infinity, right? It actually has to progressively get towards 0. You actually have to, basically each successive term has to be evaporating more and more into nothing in order for it to converge. Okay, so those two are very, very important. You need to know that the divergence one is just a little bit more robust than the convergence theorem that I showed you. We need to go ahead and just spend a few minutes reviewing properties of sigma notation, so that we have a little bit more on the ball when we start doing this. Now, remember, sigma notation. It's kind of similar to the rules of limits and derivatives and integrals and everything like that. So if I have, sigma of a sub n plus b sub n, that's sigma a sub n plus sigma b sub n. And of course it's true for plus or minus. If I have sigma constant times a sub n, I know that a constant can be moved out in front and be done like that, okay? Now, of course, that there are other things as well, but what you need to realize is that because these are true, okay, if the sigma of a sub n and the sigma of b sub n are convergent, then sigma of a sub n plus b sub n, sigma a sub n minus b sub n, and sigma constant times a sub n are convergent as well. And that should kind of make sense to us. And there are a couple, they're just, you got to remember that sometimes, the addition of stuff matters and sometimes it doesn't. You're dealing with infinite series here, okay? So you can add any constant to it, any constant to an infinite series, And let's say we have, or multiply any constant. So, you can have c plus n is equal to 1 to infinity of a sub n. And if that is convergent, and you can actually get an identifiable number for it, then all that does is just add c to that number. Okay? So sometimes you need to use the knowledge of how to actually change the form of sigma notation in an effort to be able to sort of illuminate a little bit better what's going on. Sometimes you need the sigma notation in a particular interval, so you might need to actually list out the first few terms. And so if we have something like, let's say we have, n is equal to 0 to infinity of, 2 over n squared plus 3 or something like that. If you actually list out, n is equal to 0 term, n is equal to 1 term, and n is equal to 2 term, and of course when you plug in 2, it's going to be 7 in the bottom, right? Okay. Then n is equal to 3 sigma 2 over n squared plus 3. If for some reason you needed the interval moved over here, if this is convergent, because it's simply added to a finite number right here, then this original is convergent as well. Okay? And so you need to be able to manipulate the sigma notation oftentimes in order to get it into a form. So you just need to know the rules by which you can change and alter them, where you're changing the form and not changing the value. And of course there's that very common refrain that you're used to me saying over and over and over and over and over again, because it actually is one of the bread and butter issues that we deal with in mathematics. How do I change the form of this without changing the value of this? And of course our rules of sigma notation work kind of along the lines of our rules of limits and our properties of derivatives and integrals to help us, like I said, basically change it into a form that is workable, that we can actually do something with. Now, that kind of brings our review of sequences and series to a close. That allows us to then move on to the more calculus-based new stuff in 11.3 to 11.7, which are, of course, tests for convergence and divergence of series that, basically what happens is you wind up seeing series that are not geometric and are not telescoping, and therefore, what do you do with those? And it's to that we'll turn in the next video when we start on 11.3 and the integral test. So be looking forward to that. Bye.